We present our novel method of controllable animation of fluid elements like water, smoke and fire from single still image. There has been a lot of prior works in the area of uncontrollable video generation, some mentioned here. The most closest to our domain of fluid element animation is Hoensky et al. The major drawback of uncontrollable video generation is that the user does not have any control over direction of motion. There has been some recent works on controllable video generation also, but they are either based on pokes or stochastic motion and limited to very few frames at very low resolutions. Coming to our method, given the user drawn arrow directions and corresponding speeds for each arrow, we convert it into a sparse input flow. That is, at the start coordinate of each arrow, we define the optical flow at this point in sparse input flow map as the end coordinate times the speed of the arrow. Similar to Hoensky et al., we also predict a constant optical flow for generating the video, taking the input image, the mask of the region the user wants to animate, and the sparse input flow. We use an image-to-image translator to generate a sparse refined flow. This is inspired by Howe et al., where they use input sparse ints to generate dense optical flow for video generation. However, we see that the generated refined sparse flow is very different from the ground truth average flow and not realistic. We propose a novel positional encoding of sparse hints to obtain dense flow, which is an intermediate flow and is based on simple exponential functions of distance. The positional encoding gives a flow at a particular point and is based on summation of simple exponential functions of distances of the point from the different input flow hints given by the three equations below. This dense flow provides us with a good enough approximation and makes it easier for the image-to-image translator to produce very realistic, refined dense flow. It is to note that we cannot use this dense flow directly for animation as there are visible regions of separation in the dense flow. We see that the refined dense flow is much better approximation of the ground truth average flow compared to refined sparse flow. Here we see the entire pipeline of dense optical flow prediction. This shows the entire pipeline for video frame generation. We perform feature extraction at different spatial resolutions using UNet and perform symmetric splatting using Euler integration of the constant flow, which is the refined dense flow, to generate an intermediate frame. Here we see results of our method at different stages of our pipeline. Here we see video results comparing videos generated using refined sparse flow and refined dense flow. We see that the video generated by refined dense flow is much more realistic owing to better quality prediction of refined dense flow compared to refined sparse flow. Unlike the refined dense flow is generated using exponential distance functions and not by a learning based algorithm. Hence it cannot distinguish the boundary between waterfall and the lake below, and hence moves the waterfall also in horizontal direction similar to lake motion. Here we see results of our method generated using a single input image, arrow direction and mask drawn by the user. We see that for the same image the user can draw different directions to get different animations, showing the robustness of our method to any input direction. Even though we do not have any videos of waterfall moving in upward direction, we can defy gravity by moving the waterfall in opposite direction of normal motion. Here we see results comparing our method compared to baselines of Endo et al. And modified Howe et al. We see that Endo et al. Produces stretching artifacts and our videos are better than modified Howe et al. Compared to better quality of refined dense flow compared to refined sparse flow. Even though our models are trained at low resolution, that is 280 x 512, we can generate HD videos owing to fully convolutional nature of our model. Even though our models are trained on water based fluid elements of waterfall, lake, and sea, it can also animate non-water based elements like smoke and fire. Thank you for watching.